Thank you for asking. Okay, so we're on September 17th. And we'll be talking about Newton's third law today. And Newton's third law is, I always start with the third one because then it's easier to understand the other two. But unfortunately, a lot of times we've been taught Newton's three laws of motion, and whoever taught you previously taught it the way they understand it, or the way they've seen it written before, or the way they were taught. Because that's what most teachers do, is they teach you the way we were taught. Except I try not to do that because it wasn't always the best way to go. Okay? But Newton's third law is the one that starts, most people have learned it like this. For every action, there's an equal and opposite reaction. That's how most of you have been taught that. And it's not entirely inaccurate, but there's more words that have been left out in that statement. And then we get into the fact that, are the numbers 5 and -5 the same number? Well, no. They have the same absolute value. They're both 5s. And if we were talking about moving forward at 5 miles an hour and moving backward at 5 miles an hour, they would be the same speed. But this equal and opposite thing is just not right. And then there's the rest of the words that get left out. So let's state it correctly with all the words, and then we'll talk about it some. It's what its gist is. It says that all forces come in pairs. We must have forces coming in pairs.
Like longitude and latitude?
No, like action force and reaction force.
Ah.
Latitude and longitude are ways to measure things on the globe. Okay, so all forces come in pairs. So the way it should have been stated is, for every action force, there is a reaction force on the other object that is equal in size but opposite in direction. Okay? For every action force, there is a reaction force on the other object that is equal in size but opposite in direction. That's Newton's third law. So we're going to talk about those, and we're going to talk about how we're going to diagram these. I tell my students in Physics 1, long about now, in AP Physics 1, that you can think of physics as dang physics. It's dang physics because you have to be able to describe with words. You have to be able to analyze a situation. You have to be able to numerically calculate, and you have to be able to graphically present information. So describe, analyze, numerical, and graphical with anything we do in here. Thus, dang calculus, dang physics. We do the same thing in calculus. Physics 1, Physics 2, you have to be able to do all those skills. So we need multiple representations. So we'll talk about this representation we're going to use for forces in just a second. Just a second.
One factor equal in
Size, but opposite in direction.
So basically, there's an upward force, but then there's also gravity pointing down.
But on a different object.
Oh.
And that's going to be huge in terms of how we apply this. So there's our what Newton's law says. Now, we will use force diagrams which are more properly called free body diagrams to show all the forces that act on an object. Free body diagrams. I will abbreviate them as FBDs. But force diagram or free body diagram, both of those are equally good names for what we're about to do. If you finish the Pogel from last time, you'll know that a model is something we use to simplify a problem. Because real world problems have lots of things going on in them. And we want to use models to simplify the scenario so that we're just dealing with a little bit of information at a time, not a whole landslide of information. So, let's talk about this. And let's start with a very simple situation. A book is at rest on a table. So, here's the free body diagram for the book. The first thing we do is we illustrate the book as a dot in space. We don't want to have to draw the actual physical picture. I don't want to have to draw it because I'm not very good at that. I can do boxes really well. I can make some things look 3D. But as far as drawing things, I do not want to get in a situation where I actually have to draw the object. So you can use a little box or you can use a little dot. Either way is fine. And I will do both sometimes. So what forces might be acting on our book?
Gravity.
Gravity would be a good choice. Which way would gravity pull our book?
Down.
Down towards the center of the earth. So our first force would be force of gravity. And so we would draw an arrow pointing down. If this was something that was really heavy, we'd draw a big arrow. If it was something that was moderately heavy, a medium-sized arrow. The arrow is going to indicate the size. So, for example, if I was to draw London's force due to gravity and a school bus's force due to gravity, London would get a small arrow and the school bus would get a big arrow.
Why would how?
Because they recognize the length of the arrow tells you how much force is occurring on this object.
Every time you say London, I think of the London thing, the place. And I remember always.
I know, but that's London the student. Yes, what did you say, London? Sorry. You make it as big as you feel like you should. What we really do is once we have one, then we put the other ones in there relative to the first size we pick. So what other forces might we have on our book?
We might have friction.
We might have, but in our class, we live in ideal physics land. Ideal physics land does not yet have friction. And in general, unless I tell you or the problem tells you to deal with friction, we assume that there is no friction. And I wouldn't be able to tell because this object is at rest, so I don't know if there's any friction or not yet. How do I tell if there's friction? If something's moving and slowing down, usually it's slowing down because of friction. Like if Patrick's driving his car and he lets off the gas, the friction between the tires and the road are going to cause him to slow down and stop. Jacob, hang on. Yes, what was your question or comment?
I just realized that the opposite force is the force from the book pushing up.
No, it's not, because that's two forces on the same object. Newton's third law says on the other object. So we'll have to get to that. Let's just deal with one item at a time. So, what other forces? Well, friction we might have, but we don't have it right now. We've already got gravity. What about ropes like tension or springs or something like that? Do we have any of that?
No.
Not for a book sitting on a desk. So no spring force, no tension force. The other one that you never remember because you're new to this is normal. The normal force is the keep your stuff out of my stuff force. Keep the boundary around me. So the book does not let any of the little particles from the desk come into it. None of the little book's particles go into the desk. We keep two surfaces. We put boundaries around what is me and what is you. So this force is called the normal force, and it's going to point directly upward. And so for my free body diagram to be correct, I'm going to draw these two arrows. These two should be at the same length. Because the normal force from the table upwards balances the gravitational force downwards.
Coach Wilson?
Yes, sir.
That's what I was trying to talk about. I didn't get that on the name of it.
Right, but it's not an action-reaction pair because those two forces are acting on the same object. So to do an action-reaction pair, I need another object. See, I got to have two objects to have a force. My first object is the book.
Maybe the desk.
And there's going to be two more objects in this problem that we need to talk about. One of them will be the desk or table, yes.
The floor?
Giving people time to write. Balances the gravitational force downwards, yes. Balances the gravitational force downwards. Okay. So, where does the normal force come from on the book? The book is being pushed upwards by the table. Okay? Which means, what is the reaction force for that? Book and table are our two items. Okay? Book and table are my pair. So if the table pushes up on the book, then the book must also push down on the table. So now I come over here and I go, okay, free body diagram for the table. Whatever I did here, I'm going to do the exact same thing here on the table. This is my force, and this one I'm about to draw, this is the force normal from the book. These two forces are an action-reaction pair. Those two forces are an action-reaction pair. Because, we go back to the top and look at this, for every action force, there is an reaction force on the other object. So, table pushes book up, normal force. Therefore, normal force, book pushes table down. Equal in size, so I make the two arrows visually the same length. Not going to ask you to measure these out, but try to ballpark them being the same length. So what would be the reaction force for the force of gravity? Where does the gravitational force come from? Comes from the Earth. So if there's a force from the Earth onto the book, there is also a force from the book. Don't mix in a third object. You hear? Don't mix in a third object. That's a very common mistake. So if gravity pulls me downward, I also pull gravity, which in this case I'd pull up through gravity on the Earth. So now I need a third object. So now this force has a matching force upward, and actually it's going to need to be 3. Here's your action-reaction pair for that. So this is a force from the gravity from the book. So, what does the law say?
So that everything has an action force and a reaction force.
That must be equal in
Length and strength.
in size, yeah, or magnitude, or amount, but in the opposite direction, which means this. If you need to feel powerful today, here's your physics justification for feeling powerful today. The Earth pulls us all downward, and yet we all pull the Earth upward. You do, in fact, the force that gravity pulls you down with, which we call your weight, is the exact same force you apply on the Earth upward. So if it makes you feel better, if you go and do push-ups today, you can call them earth downs, and you are actually correct.
So
Because
Chuck Norris really was pushing the Earth
when
down.
I push down on the Earth pushes back up on me. So a push-up can be thought of as I'm pushing the Earth away from me, because you are. Or you can think of it as the Earth stays still and you get pushed up by the Earth. But those two forces are exactly the same size. So then the question becomes, well, why doesn't the Earth move? It does move. But there's lots of people all over the Earth currently, and we're all pushing in different directions. So the net effect of all these forces is
Stable.
pretty close to 0. So then we get the question, what if we took all the people in the world and put them in the state of Alaska? You can actually put all of it, and energy's the other part. But we haven't gotten there yet, so I don't want to throw too many things into this at once. Okay? So, let's do another one. And let's have, let me flip pages here. speed. So in this case, we're going to have a child pulling a wagon across the ground at a constant speed. So the first thing we're going to look at is what are the forces on the wagon. And most of the time in our physics problems, you only ever work with one free body diagram. See, a lot of kids, once they finally get what's going on with Newton's third law, they say to me, Miss Wilson, how can anything move? Because if I try to move, I push on the earth, it pushes back on me with the same force. That means I don't go anywhere. I stay put. It pushes and I push it, or stalemate. The key to that is that you're pushing on different objects. And I don't know if you've actually realized this before, but when you walk forward, which way do you push? I push forwards, so I walk with like that.
Backwards.
I push and my leg goes backwards, right? And I pull with my hip. If I go backwards, I push. So how the heck am I moving forwards if my leg is going backwards?
Same thing with the car. How the wheel.
Say that again? Well, my body, but why? Oh, my head hurts.
Making
Can we
an
quit
unequal
now?
force. That's what you're doing.
I'm pushing the earth backwards. So what does the earth do to me? The earth pushes me forwards. So if we've got forces on the wagon right here, like I said, you can make this into a little block if it makes you feel better. What forces do we have on the wagon? Gravity, yes. Yes, ma'am, I will. Sorry. I didn't realize I'd scooted down. So force due to gravity down. The weight of the wagon. Wagon has a weight.
And also the kid pushing it
Okay.
forward.
So what are we going to label that force? Well, they don't tell us, like if they told us pulling across with a rope, I would call it tension. But they're probably pulling on a handle. So the general term, if we're not sure what the force is coming from is, we call it force applied. So there's an applied force on the wagon. And we usually just abbreviate that APP, but I'm going to write it because it's the first time we've done it. We're not sure what the force is. We know the kid is pulling on the wagon or pushing on the wagon or something. We don't know if it's behind it pushing it forward or in front of it with a handle pulling forward. So we're just going to call it applied. What other forces do we have? Now the ground, this time ground is going to be important, so we're going to have a ground. There's going to be two forces that come from the ground.
The upwards force.
Which is called what?
Normal force.
Force normal, and this is from the ground. This is gravity from the earth. And we also have a force friction from the ground.
But you didn't say anything about it.
But to move at a constant speed, let me throw out one of those other laws at you. There's two more laws. We're not going to do them all today. But Newton's first law says if the forces are balanced, you keep doing what you're doing. Newton's first law, in summary, says if the forces are balanced, you keep doing what you're doing. The second law says if the forces are not balanced, you accelerate. You only have two choices. Forces come in pairs. They're either balanced or they're not. If they're balanced, there's one thing that happens. If they're unbalanced, you get something else. I said this is moving at constant speed, which tells me that my forces have to be balanced. Whatever I'm doing, the forces on the wagon all add up to zero, so I'm not speeding up or slowing down. I'm just trucking along. So that means I have to have friction because there's clearly a force applied. So this is one where they didn't state friction, but you have to have it to answer the question. It's that subtle piece that happens there. Okay, so what is the reaction force for the force of gravity from the earth?
Up.
It's an upward force of gravity from.
the earth, so it's a downward force from the wagon.
So the wagon is experiencing a downwards force from the earth. We call that downwards force gravity. Therefore,